Okay, so good afternoon. And first of all, I would like to thank the organizers for inviting me for this celebratory conference. I met Toshi and probably in the Bowdoin conference on harmonic analysis on reductive group in 1989, but certainly in 1993 at the University of Tokyo, in which we had the NUS JSPS seminar on representation theory and number theory. I also paid a visit to the University of Tokyo and Kyoto University in 1996, sponsored by the JSPS. So as both events were sort of very helpful to me, and I'd like to take today's opportunity to thank Toshi and other Japanese colleagues on my generation, but also more senior colleagues such as Oshima-san, Kashiwara-san for their support and friendship. Especially in the earlier days of my academic career, and when we in Singapore were just beginning to develop mathematical research. So I'm very grateful for that. And this week's conference is, of course, dedicated to Toshi, and I would like to congratulate him for his many outstanding achievements in Lie theory, in all front, algebraic, geometry, and analytic. And I would like to wish him happy birthday for many years to come. Okay, so today I would like to sort of give a survey on theta correspondence and some of its applications in unitary representation theory. Oh, let me see. Page down. I'm trying to see how to go to page down. Okay. So the content is, first of all, I will explain some of the basic concept in this dual pair and Hall correspondence. And then I will go through compact dual pairs and stable range theta lifting. And after that, I will explain some concrete model for theta correspondence by analysis by integration. And this is how unitary representation sort of is established. And then I will explain how to do these theta lifting in an iterative way. And finally, I will speak on some recent applications of theta correspondence to what is called special unipotent representations. Okay, so here's the basic notion. If you have a finite dimensional real symplectic vector space, W, and a pair of subgroup G and G prime inside the symplectic group is called a reductive dual pair if G and G prime are mutual centralizer of each other, and G and G prime act reductively. So this was a notion invented by Hall in the 1970s. Okay, so there are the dual pair. You could have a notion of irreducible dual pair. Then all the sort of dual pair can be written as a direct sum in certain sense. So it turned out there are altogether 7 families of irreducible reductive dual pairs. And we call them type 2 and type 1. So type 2 is associated to a division algebra over R. So it could be R and C and H. And the group involved are general linear groups. So you have GLN over R, C, and H. So this is so-called the type 2 dual pairs. So the representation theory of type 2 dual pair are so slightly easier than for the second type is called the type 1, and they correspond to a division algebra with involution. So you could have orthogonal group and a symplectic group, and over the real numbers, and orthogonal group symplectic over complex number, and unitary group and quaternary group. And so these are altogether 7 families of irreducible reductive dual pairs over the real numbers. Okay, so now given a reductive dual pair in the symplectic group, we will fix an oscillator representation. So by fixing a non-trivial unitary character on R, recall that this is a unitary representation of the metapratic group, and it was constructed by Shell and Weil in the 1960s. Okay, so but we will be more concerned, first of all, for the method of Hall correspondence, the smooth representation. So let omega be the associated smooth representation, which we called it a smooth oscillator representation. Okay, and for any subgroup E inside that symplectic group, right, and we take this inverse image called E tilde, right, and define a subset of irreducible representation of E tilde as those which are realizable as quotient by the oscillator, omega E tilde invariant closed subspace of omega. So the key word is quotient. We are looking at representation of E tilde which are realizable as the quotient of the oscillator representation. So here is the fundamental and really famous theorem of Hall. It's called the Hall duality theorem, right? So you take, as it said, that if you look at all irreducible representations of the product group which are realizable as a quotient of the oscillator representation. Now it will be written, right? Then it is a graph of a bijection between those irreducible representations of G tilde which are realizable by omega, a quotient of omega, and those irreducible representations of G prime which are also realizable as quotient of the oscillator representation. Moreover, a tensor product of pi tensor with pi prime, right, which are the representation of the product group, occurs as the quotient of the oscillator representation in a unique way. So it turned out that Hall actually conjectured this in the 1970s, both for Archimedean and non-Archimedean local field. And in fact, the Hall duality conjecture for the p-adic local field were established by the combined work of Wurtz-Baget, Mingus, again Takeda, again Sun. Okay. So this is the Hall duality theorem. Now I want to explain to you sort of a slightly different formulation of Hall duality, which is a little bit more sort of concrete and direct in some way. So now you take a representation of G tilde. So we assume that's finally generated, admissible or quasi-simple. If you like, you can take the Kassaman-Wallach class, and so the pi itself, for now, it does not have to be irreducible. Right. Then you can define what is called the full theta lift of pi. So you take the oscillator representation, you take this a completed projective tensor product with dual representation, and after that you take co-invariant with respect to G tilde. Right. And part of the theorem of Hall is that this is called a full theta lift or maximal quotient is actually finitely generated admissible quasi-simple as well. And therefore, we define this theta lift, the small theta lift of pi, as the largest semi-simple quotient of this full theta lift. And so a version of the Hall-Duarte theorem can be stated as follows. If you start with an irreducible representation pi, then this small theta of pi is also irreducible, or is either 0 or irreducible. So we have sort of two objects associated with a representation of G theta, which is the full theta lift and the theta lift. So now with this theorem behind us, now the fundamental task in this subject is, two of the fundamental tasks are as follows. Given an irreducible representation of one member of the dual pair pi, and you would like to determine this theta lift, or at the very least, try to determine whether this theta lift is not equal to 0. In other words, whether this pi is in the domain of the Hall correspondence. And the other sort of is try to construct interesting, for example, unitary representation from this general formalism. Okay, so I will be speaking more on the second type, and how do you construct sort of unitary representations from this general framework of theta correspondence. Okay, so in the next two sections, I will explain some of the earlier work, sort of by now quite classical work. And the first one is about compact dual pairs. So now we have a reductive dual pair. We assume one member of the dual pair G is compact, right? Then the other member of the dual pair will be of Hermitian symmetric type. If you look at classification, it's kind of obvious. And now, first of all, I would like to explain that this covering of G theta is not really serious in the following way. So in fact, there is a character of the two-tier one-dimensional representation of this double covering, such that if we twist the oscillator representation, right, by this Kasai inverse, in fact, it will factor through the linear group. Therefore, the representation which occur with this restriction are in fact of the form a certain this character time a representation of G. Okay, so in this slide, and this is the classical work of Kashwara-Vern and Hall. So Kashwara-Vern proved this theorem for the sort of very concrete cases, and Hall established this result on for an abstract dual pair. Okay, so in this case, things are relatively simple. So the restriction of the unitary representation, right, this is omega chat, to this product is a discrete and multiplicative free sum. So we have the decomposition as a unitary representation is a direct sum over all irreducible representation of G. Right, so we have Kasai tensor with sigma. Right, this is Kasai is this one-dimensional character I just mentioned, with the external tensor product L sigma, where in this case omega sigma is always an irreducible unitary lowest weight representation of G theta. Now, of course, it can be equal to 0. Right. So the decomposition is the finite and the multiplicity sum. Okay, so when this sigma occurs in this particular L2 correspondence, can be directed, can be detected in the so-called space of harmonics, which is a multiplicity free representation of the compact group G product with the maximal compared subgroup K prime of G prime. Fine. And the map from sigma to L sigma is injective in its domain, right? And is described explicitly by this pairing of sigma with the lowest K type of this unitary lowest weight module in the space of harmonics. So in other words, all the information is hidden inside the space of harmonics. And this decomposition of space of harmonics according to the representation of G and K prime can be described explicitly and in a relatively simple method. So this is classical work of Kashwarvan and Howe. I'll give some simple example. So if you take G and G prime to be orthogonal group and syncretic group, right? So now in the case when P is less than or equal to N, and later on we will have a notion called stable range. This is in fact the stable range, and it turned out that every irreducible representation of the compact group G over P, which is P, occurs in this dual pair correspondence. And when P is strictly bigger than N, and this sigma occurs in this dual pair correspondence if and only if sigma occurs into the L2 of OOP divided by OOP minus N. So this is usually called Stifel manifold. Right? So it occurs if and only if sigma in the harmonic analysis for this Stifel manifold. Okay. Now, furthermore, if P is very large, P is bigger than 2 over N, and then omega L of sigma, which occurred, are in fact members of holomorphic discrete series. So these are some of sort of easily remember facts about this dual pair correspondence. Now, I would like to mention say a bit more about unitary lowest weight representations and in relation to this general Howe correspondence or Theta correspondence. Right. And if you take G prime to be the real syncretic group or unitary group, so this is Hermitian symmetric type. It was a result of Enright particularity that all irreducible unitary lowest weight modules L G prime theta arrive in this manner. In other words, by taking a compact dual pair, you take all the possible G's, which you form a dual pair with G prime, and you do this decomposition, and you are going to get all the irreducible unitary lowest weight module representation of this G prime. So this is for the case of real syncretic group and unitary group. Now, in the case when G prime is equal to O star 2 over N, there are some minor exceptions, but more or less the picture is still sort of same, with some minor exceptions. Okay, so this is so in other words, right? For the irreducible unitary lowest weight module can all be realized more or less in this dual pair kind of formalism. Okay. Now, I would also like to mention that Enright, Howe, and Waller classify all irreducible unitary lowest weight representation or any covering of this G prime in an internal way without reference to other groups. Okay. Okay. Now, the last item is some. Because of these explicit realization of unitary lowest weight representation, and it was Nishiyama, Ochai, and Taniguchi, and use these models of irreducible unitary lowest weight representation from Hall correspondence to determine the associated cycles of all such representations. Okay, so the point is this particular realization of unitary lowest weight modules through Hall correspondence is really sort of capture these associated cycles, these a very important invariant in a very, very nice way. So now I want to explain to some another scenario where unitary representation enters strongly, and this is so-called a stable range theta lifting. So we take what is called a type 1 irreducible dual pair G and G prime. So both and G prime are the isometry group of certain Hermitian forms, right? Over this division algebra, one of them Hermitian, the other skew Hermitian. Right? We say that G and G prime is in the stable range where G is a small member if the following is true. You can find in the totally isotropic subspace of V prime such that the dimension of the full space V is less than or equal to the dimension of this totally isotropic subspace V1 prime. And a good notation is the following. I write it as 2G is less than or equal to G of prime. Right, so the group is, in a certain sense, is at most half of the size of G prime. So this is called a stable range where G is a smaller member. And then the work, some result of Hall and Lee are as follows. Suppose G and G prime is in the stable range where G is a small member. Then Hall correspondence, in fact, give rise to an injection of the full unitary dual of G prime, and here I have this this genuine part. So in other words, those genuine representation of G prime, this is a unitary dual, right? More or less, the full unitary dual, right, will inject to the unitary dual of the other group through Hall correspondence. Okay, so the key message of this result is as follows. Right? So the genuine part of the unitary dual, in fact, is in the domain of the Hall correspondence. This is the first message. The second one is the stable range theta lifting preserves the unitarity. Okay, so for this, okay, and one could understand more concretely about this stable range theta correspondence through Mackey theory. So this is as follows. So this is a work on Hall and Lee, and in the 1980s, perhaps in the as well as early 1990s. So you fix in totally isotropic subspace V1 prime of V, so with the same dimension of the standard module of G dimension. And then you take P prime to be the maximal parabolic subgroup of G prime, which preserves the V prime plus star. Okay, so this is star for convenience with this unipotent radical N part. Okay, now so this maximal parabolic subgroup will contain as a subgroup the following: the general linear group over V1 prime of star times this unipotent radical. Right. So and of course, because the equality of the dimension V with V1 prime and this isometry group of this G here can be embedded, so can be considered as a subgroup of GL of this V1 prime of star. So at any rate, we have certain subgroup H of prime inside this maximal parabolic subgroup. Now it turned out that the theta left, which is an irreducible, of course, in this case, will be irreducible unitary representation of G prime, is in fact already irreducible under restriction to this H prime of Theta, the subgroup. And this restriction to this H prime can be realized as induced representation from the subgroup G prime and prime to this the product of general group time n prime. Okay, so this is so right hand side in some sense, this is the irreducible unitary representation, which you can understand by Mackey theory. So I won't explain sort of more details, and but except to say that you can describe that the restriction of the theta left to this subgroup, and it can be realized as some kind of induced representation, which involve pi of Chet. So this is sort of a more concrete way to understand this stable range theta correspondence. Another notion which is very useful in this topic is this House notion of rank for an irreducible unitary representation of a classical group. So this notion is defined in terms of Zn spectrum, where n is the unipotent radical of certain maximal parabolic subgroup P of G. So let's take an example. Let's take G to be this metapratic group, and this you take P to be the zygote parabolic subgroup, and the N is a unipotent radical. So it's a abelian group, which is isomorphic to the space of n time n symmetric matrices. Okay, so this notion of rank allows us to decompose this unitary duo into parts, which is called this is a unitary duo with pure rank R. Right, so it's a theorem of how that any irreducible unitary representation will have a pure rank. So so this notion of rank is well defined, and furthermore, among those irreducible unitary representation with pure rank, which is strictly less than n, you can have finer decomposition. You can break it into the parts which are indexed by certain n time n symmetric matrices. So these are the parts where the n spectral type is of a fixed type, which is given by beta n time n symmetric matrices. So this is how also show that the larger the rank of irreducible unitary representation, the faster its matrix coefficient tend to decay. And this assertion can be understood as viewed as a quantitative version of the famous Hahn-Mohr theorem, which said that for an irreducible unitary representation, and which is not one-dimensional, and so the matrix coefficient will decay at infinity. So this is this notion of the rank will in fact provide further information about the quantitative way how fast the matrix coefficient is going to infinity, going to zero. So here is a result of Lee, and here I put the classification because it's quotation mark because this which I'll explain later. Okay, so this result of Lee said that up to unitary characters, all so-called low rank irreducible unitary representations of G prime. So in the case of metapratic group, low rank, it really means the pure rank is strictly less than n. So all irreducible low rank irreducible genuine representation are obtained by theta correspondence from a G, where this G is, something like strictly stable range, when 2OG is strictly less than G prime in a precise sense. So in the case of metapredict group, it goes as follows. Recall that we have in a symmetric matrix beta or rank n. Of course, it's going to determine an orthogonal group of signature P and Q, where P plus Q is equal to R. And then the representations where this n spectrum is concentrated on this particular beta consists precisely of theta lift of irreducible unitary representations, which come from an irreducible unitary representation of OPQ. So this is a part of unitary representation theory where the theta correspondence is playing a very crucial role. It's said that among the irreducible unitary representation of classical group, there are parts, right? The relatively singular part, which that you will need to need to understand through how corresponding in a certain sense. Okay, so now I want to speak more about this unitary representation. So how do you establish unitary preservation in this context of theta correspondence? Here is a general idea. So this is providing a model for theta lift through integration. So the general idea is as follows. You take a representation of GO tutor, and then you consider the following integral, basically. So it's essentially a matrix coefficient of the oscillator representation and a matrix coefficient of the representation of pi. You take the integral, right? Suppose it is absolutely convergent. Right, this integral. Then it clearly is going to yield a bilinear map, right, in the following space. Now, if you start with, if the pi is unitary, so you could use, pi bar to replace pi chat, and then this form here it will become a G prime invariant Hermitian form on this completed tensor product. Form. So now if you take the left kernel of this form and you divide it by this tensor product by this left kernel, and you get what we call a theta of bar. So clearly it's a quotient of the full theta lift. Therefore, it's going to be a representation which is finite generated, etc. Okay. So the challenge to establish a unitary preservation in this particular way of looking at how corresponding is as follows, right? And you need to show that theta bar, in fact, is non-zero, right? And you also need to show that induced Hermitian form on this quotient is, in fact, positive definite. And below are two of the cases where this method is successful. So the first one is due to Lee, and this is exactly the case, so-called a stable range. Within the stable range, for any this unitary representation, you can establish these non-vanishing and positive definites, etc. And as well as for the case when pi is a discrete series, when the dimension satisfies this simple equality. This is the first case. And the second case is due to He, and it's for the case of so-called strongly semi-stable range. Semi-stable range. So this is a general way to establish unitarity in the context of Hall correspondence. You take matrix, so the integral on matrix coefficient integral, and you try to show both non-vanishing and positivity. So the next slide, I will explain a general result on unitarity preservation, and I'll be a bit sort of informal, and we come up with certain notion of converging range based on suitable bound of a matrix coefficient, and assume some mild condition on the sizes of the two groups involved, and a mild condition on the pi. In fact, we can establish as a general fact about how correspondence, that if pi is unitary, and this particular model of theta bar is also unitary. Okay, so now if you can show that this particular model is unitary, and since it's unitary, clearly it's semi-simple. It's a quotient of this 4 theta left. So as long as if pi is irreducible, if you can also establish that this is non-zero, then how duality theorem implies that this the theta left is exactly given by this particular quotient and is irreducible, right? So the key thing in order to push further is to understand whether this theta bar is not equal to zero. It's equal to zero. So perhaps I will just give an indication how this theorem is proved, and we use the following general result of Harris, Lee, and Sun. And it goes as follows. If you have a real reductive group with a maximal compact subgroup K, right? So you take two unitary representations, pi 1 and pi of 2, and pi 1 is arbitrary, but pi 2 is weakly contained in the regular representation. Okay. Now, so you take vectors in the first unitary representation and assume that its matrix coefficient integrate against the Hersheimer psi function is absolutely convergent. So you take the first unitary representation, you just take any kind of matrix coefficient, but the requirement is you integrate against this Hersheimer's psi function is absolute convergent. And for the second representation, you take any finite k finite vectors, and then right. So in the tensor product, of course, you take this inner product, tensor product, inner product, and then you make this diagonal matrix coefficient. You integrate again this group. It turned out that under these circumstances that it will be absolutely convergent. It will, and more importantly, it will be a non-negative real number where U is sort of decomposable kind of tensor vectors. So the key for this hypothesis is the second representation is weakly contained in the regular representation. And then, you know, the first one can be any arbitrary unitary representation, and you do this simple integral of this diagonal matrix coefficient. So this is source of the proof for our general unitarity result. Okay. At any rate, if you use these suitable converging range, you could do this theta lift a number of the times, iterate theta lift. You start with a unitary representation and assume this unitary representation has, you know, is in certain converging range, and then you are guaranteed to get the unitary representations. So you could keep doing that, and you get many interesting unitary representations. Okay, so finally, I'm going to explain that recent work of Babish, Ma, Sun, and myself, and it informally state is as follows. Right? You start with unitary characters, unitary character, and then you can obtain in this fashion by this iterate theta lifting or special unipotent representation of real classical group, assuming some condition on this nilpotent orbit with some parity condition. In fact, this picture applies also for the real metropolitan group, where we replace special unipotent representation by metapredic special unipotent representations. So we have a corresponding notion of metapredic Babish-Vaughan duality, which is similar to the Babish-Vaughan duality for reductive linear groups. So this is doing iterated theta lifting. Okay, Chair, how much time do I have?
You have 20 minutes.
Oh, okay. So I'm okay. So thank you. Okay. Now, especially when you have to do these theta lifting a number of times, it's very important to have good control of the lifting process each step of the way. So here, the basic idea is that's sort of well known is to understand how fundamental invariants such as infinitesimal character and K-types, especially in this the space of harmonics, and how K-type behave under theta lifting. So this is a general idea. And I would like to argue that, in fact, other fundamental invariants, such as associative characters of Vaughan and generalized Whittaker models, should all be utilized. So this is an idea that has not been sort of explored very fully in the earlier investigation of theta correspondence. Now, and the key for doing this, right, to exploiting these fundamental invariants is in something called the moment maps. All right. So I will give two results without explaining all the notation. I'll give two results in this direction. Right. So recall that Vaughan has this map, right, starting from finite Hersheimer representation to this associative character. So this is called associative character. So this associative character is sort of a refined version of associative cycle, where a lot of people are familiar with. It turned out that in the theta lifting setting, the associative character of Vaughan can be estimated having the upper bound by geometry, by something called the geometric theta lift. So here is a result which I want to give as a flavor of this kind of result. So you take two orbit O and O prime. One of them is called the descent of the other one. Essentially, these orbits are O is something slightly larger than O prime. So by adding a column to this O prime, essentially. Then you recall that we have this full theta lift, theta of pi of prime, and you take the associative characters A of C, and in fact is always bounded up above by certain geometric process, right, applying to the associative character of pi. Associative character of pi. So the associative character in the theta lifting will always have an upper bound, right? And in many good circumstances, you can show that in fact this is an equality, and that is to show an equality is more involved. But in general, we always have an upper bound. So this is for the case of the associative character. Now, another fundamental invariant is generalized Whittaker models, which are associated with nilpotent orbit. Right? In fact, you always have an equality again by geometric theta lift, but this time in terms of nilpotent G orbit, not Casey orbit. Right? So a result that I proved with Gomez a number of years ago is quite similar. Right? So you take space of generalized Victor models for this full theta lift. In fact, it's isomorphic as certain module for the sort of stabilizer group with space of generalized Victor model coming from them, right, on the G side. So this is at G prime side, this is G side. And this equality is very effective in showing the non-vanishing, right? You want to show that certain theta lift is not equal to 0. And if you are able to produce a non-zero functional, and then you are done. And this is a very good mechanism to showing the non-vanishing, right? Non-vanishing. Okay, so this is sort of two of the things that we use in order to control that iterative theta lifting. And finally, I have this I would have this application for this iterative theta lifting and to produce all special unipotent representations. So here's the table. Right? So we have all real classical group. Here I have excluded a complex group. The reason is, I counted these number of the group exactly. There are 10 of them. 10 is good. So you have a general linear group GLN of R, GLN of H, unitary group, and it's double covering. In orthogonal group in all dimension, orthogonal group even dimension, real symplectic group, metapredic group, and as well as quadratic groups. Right, and so the right-hand side are the Langlands dual group. These are complex group, and except that in the case of C tutor, where this is metapredic group, right, and we have its metapredic dual, which is sp2n of C. So this is slightly different, but actually it turned out that everything fit together in a very nice way. So this we have these 10 groups, right? Okay, so in the next few minutes, I just explain this notion of special unipotent representation. So you start with a nilpotent orbit in the Langlands dual, G-O tutor. Sometimes it could be a metapredic dual. And you embed this nilpotent orbit in an STL2 triple, and then you take a neutral element, is this H, take half of it, and it will determine an infinitesimal character. You call Kasai or Cheng. And then by a theorem of Dixmuir, there exists a unique maximal ideal with this infinitesimal character. So you call the I of Cheng. And then, of course, the associative variety of this is a closure of certain nilpotent GC orbit. And this O here is called Babish-Vogel dual of Cheng. All right? And it is special in sense of the Lustig. Now, this framework works perfectly for the metapredic group, and all you have to do is to replace this Babish-Vogel duality by metapredic Babish-Vogel duality. So anyway, we have a maximal ideal associated to this nilpotent orbit in G-chat. So, and an irreducible Casimir-Wallach representation pi of G is said to be special unipotent attached to O-chat if this is maximal ideal I over chat annihilates pi. So the set of equivalent classes or irreducible Casimir-Wallach representation which are special unipotent attached to O-chat is this notation. Okay, so in two prepring, we parameterize and explicitly construct all special unipotent representation of real classical group, GLN, etc., right? As well as metapredic special unipotent representations of the metapredic group and the complex symplectic group. The first paper is about counting and reduction to parity, and the second paper is about construction unitarity. So I will just explain a little bit how all the steps involved in construction of these special unipotent representation. First of all, you count the number of elements inside the set by combinatorial object. And this is quite involved. It involves coherent continuation representation, CLN or primitive ideal double cell, Hersheimer cell, branching law of Y group representation. So, and the second step is reduce the problem of construction to the case when this OO check has good parity. So in general cases, you just have to start with good parity, and then after you get all the representation with good parity, so when O check has good parity, then you just do irreducible parabolic induction. And this is the tool we use is Cauchy-Dunlop-de-Vaughan. And the key step is to construct representation in this special unipotent representation by iterated theta lifting whenever the OO check has good parity. And in order to define these representation, we develop some combinatorial thing. It's called the combinatorial descent. And after we construct all the representation, we have to, because we have the counting, and we would like to distinguish all the representation constructed by Vaughan's invariant, which are the social characters. In the tool, we use moment map, geometric theta lifting, doubling method, degenerate principle series. So both the step that I have labeled star and star are complicated steps. And after that, this will establish the exhaustion. So, excuse me, yeah. Okay, so because we have the construction and exhaustion, and we are able to prove that the following theorem, this is a confirming conjecture, Arthur Babish-Vaughan for real classical group, all special unipotent representation of real classical group are unitarizable, and all metapletic special unipotent representation of SP Tudor and complex are unitarizable. And okay, so in the special case where the classical group is quasi-split, and then you have Arthur's classification theorem, and so you have the definition of the Arthur packet. In this case, and Adams and his collaborator have established the unitarity as well for this particular case where the Arthur packet is well defined. So the Arthur packet is in fact equal to ABB packet. Okay, and I would just like to, in the last 1 minute, I would just like to highlight sort of the other result that we obtained beyond unitarity. In fact, we determine the social character of any special unipotent representation. And also when this O check is quasi-distinguished in certain sense, then the associated character map, in fact, induces a bijection of all the special unipotent representation attached to O check with this unmissable orbit data over this complex orbit, where I have precisely defined the AOGOO. For the complex one, it will be by disjoint union of the set of isomorphic class admissible orbit data over KC orbit that's right. And this quasi-distinguish is in certain particular sense where you look at rows of these orbit. Right? So in certain cases, you don't want to have an odd eye such that these two rows are the same. In certain other cases, you don't want to have an even eye such that these rows are the same. So this is called a quasi-distinguished unipotent orbit. Okay, so with that, I would like to end my presentation. Thank you very much.
Thank you very much.